Hi, everyone. Welcome to the session. We're going to be kicking it off with efficient Chad. I'm going to turn it over to Tom, who's going to tell us all about his work.
Yes, thank you. This will be a talk about automatic differentiation, in particular about the algorithm called Chad. So in this idea of automatic differentiation, which I will be shortening to AD because the name is kind of long, specifically in reverse mode AD, we're interested in a program that takes in a number of real numbers and returns a single real number. So we're considering this as a normal mathematical function, right? A thing that takes a bunch of reals and returns a real. We might be interested in its derivative, specifically in its gradient. This is a function that takes in the same kind of input and returns a value in Rn, which is the gradient of this original function, considered as a mathematical function. It just happens to be implemented as a program. And reverse mode AD refers to a family of algorithms that tries to produce gradient programs that compute these derivatives efficiently and in a way that is numerically stable. And for these reasons, reverse AD algorithms are very useful in a variety of disciplines. And it is this idea of efficiently that I will be talking about more in this presentation, specifically about the computational complexity of this gradient algorithm. So as the PL community, when we think about reverse AD algorithms, a number of things that we might be interested in is asking whether these algorithms are correct, so whether we can reason about them. For that, it also helps if the algorithms are compositional, because then they're easier to think about, they're easier to extend. And if you want to extend these things, you're probably also interested in thinking about whether they are flexible, whether they can handle a variety of interesting input languages that have various kinds of, interesting language constructs. Moving down the list to more practical concerns in a certain way, we're also interested in these things having correct time complexity, and what exactly that means, I will be elucidating a few slides further on. We're interested in whether these things are parallelism preserving, because in many applications of AD, you're interested in situations that have lots of data, you have programs that are parallel, and you want their derivatives to be parallel as well. So we want to preserve the parallelism when differentiating programs. And finally, of course, you want, the programs to be practically efficient as well, which is, I guess, a very practical concern. So there is this Chad algorithm, which has a variety of nice theoretical properties, but so far it did not have the more practical properties on this list. And in this work, which is called Efficient Chad, we tackle these two, which are about the correct time complexity and about the parallelism preserving aspect. So this part, where the time complexity is preserved, we have proved this formally in Agda, and you can see the details about that in the paper. This part is future work, but the fact that we want this to be practically efficient as well is always in the back of our minds when thinking about the transformations that we apply. So let's look a bit at Chad and see what it means. Right? So we had this situation where we're thinking about a program, and we had this gradient program that we wanted to get out. In order to make this compositional, we have to generalize this a little bit. In particular, instead of immediately producing this gradient, we want there to be an additional argument, which is sort of the derivative of the function result, and we want to push this backward through the function to get back at the input, which is then the derivative of the input, which is the gradient. So now that we have this separate argument, we can generalize this a little bit. And now we can handle functions from Rn to Rm, which is already a bit better. Now, unfortunately, not sure if it's unfortunately, in AD, what you're doing is you're applying the chain rule many times over and over. And in the chain rule, it turns out that you need the original value of all the intermediate points in the program. So in addition to this backpropagator, this function from Rm to Rn that we return here, we also need what's called the primal value, which is the original value of the program at this point. So we return a pair here. And then we can generalize a bit further. We can generalize the domain to sigma. We can generalize the codomain to tau, where these primed versions are their derivative types. And now we basically have arrived at the type of Chad. So the only thing we need to do is generalize this sigma to the context gamma. And then we have Chad, which takes in a term in the context gamma and of type tau. And then the code transformation returns a new term in the same context, which produces a pair, which is the original function value and this backpropagator. And this D2 type transformation is a mapping from types to types, which produces sort of the type of derivatives of this type. So what do I mean when I talk about the correct time complexity? So in the imperative world, this is a concern that is relatively easy to express. If you have a program which consists of a number of steps, then the derivative program will also consist of a number of steps. And first, you're just going to do the steps of the original program in order, saving the intermediate results. And then afterwards, you're going to do the steps in reverse order, the derivatives of these steps, which are going to reuse earlier results, right? And so because of the properties of how large these steps are, you can see that the size of the program on the right is proportional to the size of the program on the left. So the time complexity is like you have a constant factor overhead from this transformation. And this is something that you want, but this doesn't at all translate to the functional world because contrary to this, we're not interested in sequencing things, we're interested in nesting things. That's what we do when we talk about functions. So what happens when we look at something like Chad? This is a type of the Chad program transformation again. So let's look at one of the rules. This is the one for variable references. If we have a variable reference x of type tau, then the transformation of this is, of course, a pair, because we need to produce a term which is of pair type. The primal of this is simply a variable reference again. And the backpropagator here, the dual, is a function which takes in the derivative with respect to this variable reference. And it needs to produce a derivative with respect to the context, which in this case is simple. It is a one-hot vector. It is a vector that contains this value d at the place that corresponds to x and zeros everywhere else, abstracting a little bit over how exactly this d2 of gamma is represented. The second thing that we can look at is the derivative of a pair projection. So first, in this case, so we first compute the derivative of the term t, which produces this x, which is the pair, and this f1, which is the backpropagator of this pair. And then what we return is a pair consisting of first x, which is the primal value of this term. And we return a backpropagator, which takes this derivative d with respect to the first component of the pair, then builds d comma 0, which is the derivative with respect to the entire pair, and then passes that thing to f1. This is all well and good, it seems. And you can look at the rules for many of the other constructs as well, but I will not go into those in detail. The things that I want to highlight is that in order to get some kind of inductive proof of this time complexity property here, we would like the right-hand sides to be proportional in time to the left-hand sides. And is this true? Well, not quite. There's a bunch of things here which are too expensive. So what we would really like here is if, apart from all of the subterms, right, the transformed subterms only occur once on the right-hand side. So you really want all of the other work that happens on the right-hand side to be proportional to all of the other work that happens on the left-hand side. And it happens to be all constant time, so you want all the other work to be constant time on the right-hand side as well. Is that true? Unfortunately not. There's a bunch of operations that are not. For example, these one-hot vectors that I was talking about, they are much more expensive now, or at least in a naive representation of things. You have a variety of zeros that you need to create, both of normal derivative values as well as for environment derivatives, these d2 of gammas. You need addition of a variety of things. You need addition of normal derivative values and also additions of environment derivatives. And both of those are fairly expensive. And finally, here at the bottom, you also need to split an environment derivative in the derivative component that belongs to the thing that you just bound, for example, in a lab binding, and the rest of the context. So you need this for scoping operations. All of these things are now expensive, or most of them are, and we need to make them cheap. Thank you. So on the right top of the slide, you see a list of operations that we need to make relatively efficient. So the first thing that we're going to do is we're going to look at the zeros. And to tackle the zeros, to make them efficient, we need to add sparsity to our definitions. So far, the derivative of a pair was simply a pair of derivatives, which means that if you have a sparse derivative of some relatively large product structure, it looks like this. There's a whole bunch of zeros in there. And what you actually want is you want to represent that sparsely. For a whole subtree that is 0, you just want to cut that away and prune that and say that it's 0. So in effect, what you want is you want this. You want to stick a maybe in between this layer of the tree and the rest. So in essence, you're adding a point to this derivative type, which represents a 0, so that you can sort of inject a 0 somewhere cheaply. What this does, right, and then the other thing that you want to do is you want to do the same thing for environment derivatives, which are essentially large products. Right? It's a vector, it's a large product of environment of derivative types. You can represent that sparsely as well by using a map data structure, which is essentially a sparse vector. So what you get from this is you get that zeros are now constant time. Yay, we've done 2 out of 6. And also it turns out that one-hot environments and splitting environments is also constant time, so we're actually 4 out of 6. We're well on our way. Second thing that we're going to do is we're going to eliminate all uses of environment vector addition. How are we going to do that? We're going to do that by state passing. So instead of creating lots of environment derivative vectors in a variety of places in our derivative program, we're going to create one at the beginning of our derivative program, in the beginning of our first backpropagator, so to speak, and then pass it through the program, adding individual contributions to it as we go, and then in the end return the result. So we can do this by lifting the backpropagators to monadic code, and all that changes is, well, a lot of the program transformation doesn't change, and in the backpropagators we need to lift that to monadic code. But we know how to do that as PL people. There's nothing really interesting going on here. There are a few individual operations that you have to reformulate into something else, but there's a local changes, and the only global change that's happening is lifting to monadic code. That's it. What do we get? Well, we don't have environment addition anymore. So, yay, I guess. And then the final thing is that we still have additional derivative values that we have to fix, but I am claiming that we don't have to fix that. Because this slide says complexity proof. So let's just go through this and we'll see where it ends up. So if you want to write a complexity proof for this, you need to have a cost model relative to which you write this complexity proof. So in the formalization, we wrote an interpreter of our simple extended lambda calculus that also returns the number of steps that were taken in evaluating the thing. And then we have a very conservative, simple cost model that does the job. You try an inductive proof, which is, of course, the thing that you want in this setting. It doesn't quite go through because you need to generalize the induction hypothesis a little bit. This is usually not surprising, but the way that we do this here is slightly finicky. It turns out that there's a fairly subtle argument that you can give. Well, whether this subtle may depend on subjective preferences. There's an amortization argument that you can give. In particular, you can amortize the addition of the environment of derivative values against their creation earlier in the program. And just for the experts, this happens to work because you're passing those around linearly in a certain sense. So the amortization argument does end up working. This is the reason why I wanted to formalize this, because this felt tricky. So that means that basically without work, we have made the last operation efficient because we could amortize its cost away against other things. Finally, the last thing is that there were a bunch of logarithmic factors in the complexity that we accumulated because we chose a sparse tree value as the representation of environment derivatives. So we replaced those with a mutable array for which we, again, don't need to change the code transformation because it is already a monadic form. We just extend the monad a little bit. And then we are done, and then we're happy. Yay. So this is my final slide. There's a bunch of things that did not fit in this presentation, but that we do have in the paper. For example, we have coproducts and the dynamic control flow in the paper. We have arrays and parallel programs. And we have higher order programs, which you can make efficient by closure conversion for the chat enthusiasts. where I unfortunately have to note that the Agda formalization of the proof is only the base language, including co-predicted conditionals, and it does not extend to arrays and higher order functions yet. And in ongoing work, well, we might want to extend the proof, and there's also a list of other things that we might be interested in. So thank you.
Great. We have some time for questions. Does anyone have a question? Yeah.
Thanks for the talk. At the beginning, you make it sound like sparsity is important, but then in the end, you replace the sparse tree with a mutable array. So could you tell the whole story without mentioning sparsity at all?
I see. Good question. No. Sparsity is important. And in particular, for simple product types, we keep the sparse representation. You do need... Well, so there's a tension here between wanting a representation that you can in constant time add stuff to, and specifically for environments that you also need to split elements off, right? So you can have sort of a free you can have a free monoid representation of a variety of things, and that works for most things except for the environment derivatives because you also need to split stuff off. And that's why we need a mutable vector there. For arrays, you do end up with sort of free sparse things.
Great. So there's a formulation of this work where you don't have explicit environments, but where you do with point-free notation instead, and then you basically implicitly thread the environment through. Would that make any change to how you would reason about complexity?
So you're thinking about the combinator representation of
this?
Yes. Yeah. I haven't looked too closely into that, but the first thing that I concluded when looking at the combinator representation of this algorithm is that the translation from lambda calculus to combinators is not complexity preserving, and at that point you've sort of already lost. So I looked at the lambda calculus version only.
Thanks.
Any other questions? I have one quick question maybe for you. This is a beautiful result that kind of is very deep and very technical, right? It's showing that, that you've actually preserved this complexity of the reverse mode differentiation. I'm curious, do you see a pathway for this into potentially tools, right? I'm asking you a very hard question here, but I'm curious just to hear your high-level viewpoint on this, to just kind of see where you think it's going, right?
Yeah, I hope that later in my PhD I will be able to write exactly that paper, but who knows, right? No, there is, the things that I'm presenting here are very much fixing the complexity of this algorithm, but are not necessarily super efficient. So I should definitely add a disclaimer that there are, of course, lots of practically efficient reverse ID algorithms that are used in practice. And the reason that I'm not looking at those is because this one I can actually understand as like a single person. I don't need 100 Google engineers to understand the algorithm. So how I think about this thing being maybe at some point practically efficient. So the first thing that you have to do is there is this here. If you look at the rules, there's lots of lambdas here. You want to get rid of those lambdas because you're introducing higher orderness where there was none. It turns out that you can, so that's good. You want to partially get rid of the sparsity, like locally, because adding lots of maybes is probably not a good idea. I hope that a compiler pass will help there. I have some other ideas, but it's a bit fuzzy so far.
Perfect. Thank you so much. Let's thank the speaker again.